So the polarity usually happens in the bonds, in the covalent bonds, when there is difference in electronegativity between two different atoms. If I have atom number, or we call it X, and atom Y, and there is difference in electronegativity, its ability to attract the electrons of the covalent bond to itself, this makes one of them more electronegative than the other. So if Y is able to attract electrons of the covalent bond to itself more, it will be more electronegative. And in this covalent bond, it will take a partial negative charge, while the X, which has lower electronegativity, will have a partial positive charge. Now, for example, I have chlorine atom and the carbon atom. The chlorine atom is much electronegative than the carbon atom, so it will attract the electrons of the covalent bond more towards it. This will be partially negative, and this is partially positive. In this case, we will call this bond a polar covalent bond. This means that the chlorine is attracting the electrons of the covalent bond more to it due to its higher electronegativity. This means that the electrons of the covalent bond will spend more time around the chlorine atom more than the carbon atom. So this is called a polar covalent bond. If the atom has two similar atoms, like it has chlorine and chlorine, these two are similar atoms. There is no difference in electronegativity between them. The pull of the electrons from each of the atoms to itself is similar. So there is no difference in electronegativity. So the electrons spend the same time in this chlorine, with this chlorine, at this time with this chlorine. So there is no partial negative or partial positive charges, and it is called the non-polar covalent bonds. The polarity causes something called a dipole. So this is a dipole. This is one pole, and this is one pole, negative and positive poles, causing formation of a dipole. Positive and negative forms a dipole. So the dipoles are found only in the polar covalent bonds, but not formed in the non-polar covalent bonds. This is because they are either identical atoms, or they are two atoms which are not identical, but they have very similar or very close electronegativity. Electronegativity between them is not that big. Now, this is what we explained is the bonding of the polarity of the bonds. But what about the polarity of the molecules itself? The molecule can be polar or non-polar. This depends if it has polar bonds inside it or no. And we have said that if the molecule has polar bonds inside it, it might be polar or non-polar. It depends on if it is symmetric or asymmetric. So the symmetric types of molecules, with like the tetrahedral shape, like the trigonal planar shape, these are all symmetrical shapes. They have symmetrical shape, and they don't have lone pair of electrons in the central atoms. Most of the molecules that have no lone pair in the central atom are symmetrical shapes, and the total molecule is non-polar. Why is that? Because the polarity cancels. The polarity cancels, and also in the linear shape, like carbon dioxide. So linear, tetrahedral, and trigonal planar, they are all symmetrical shapes. They are non-polar molecules, while the polar molecules happen when there is a asymmetrical shape. So asymmetrical shape, like the bent or the V-shaped molecules, the trigonal pyramidal shapes, these or most of the molecules that have lone pair of electrons on the central atoms will be asymmetrical shape, and they will be polar molecules. Let's take this one as an example. We have carbon in the center and fluorine from all the sides. The fluorine and carbon actually is a polar bond, so there is a difference in the polarity. This is partial positive and this is partial negative. But the polarity of this one, which is usually drawn in the form of arrow going from the carbon to the fluorine, the arrow shows which atom is more electronegative. So if I have, for example, carbon and fluorine, or carbon and oxygen, or carbon and nitrogen, the difference in electronegativity shown in the form of an arrow which goes from the less electronegative element to the more electronegative element, and this will be partially negative and this partially positive. If I look at a molecule like carbon dioxide, this is a polar bond because there is difference between the carbon and oxygen electronegativity, and this one is also polar because there is difference in electronegativity, but this polarity cancels out. So is this a dipole? Yes, it is. This is a dipole. It is. But because this is a linear shape, as we have explained, in the linear shape, the polarity cancels each other. So the molecule as itself, the total molecule is nonpolar. So the bond is polar, but the total molecule is nonpolar. How we will know? Again, if there is lone pair of the electrons, most of the structures which have lone pair on the central atom are symmetrical and they are nonpolar. And there is some exceptions to that we will mention. For example, this one is also has lone pair on the central atom, so this is a trigonal pyramidal. But there is an exception, is this shape. This shape is having lone pair on the ZeF2. It has lone pair on the central atom. Still, it's not polar. Still it's polar. So it is. Mister, you said that the ones that have lone pair on the central atoms are symmetrical, and they are symmetrical, and they are polar. But this one is an exception because it is non-polar. It's non-polar because the polarity cancels out. So although there is lone pair of electrons here, but still this is a non-polar structure. The next point that we will revise is the intermolecular forces of attraction. The intermolecular forces of attraction, or what we know as the IMF, exists between molecules in a covalently bonded substance. So these forces, what we need to be broken apart in order for the covalent substance to change its phases, change from solid, for example. In order to change from solid into liquid, then you have to break the bonds between these solid particles and change it into liquid. And again, if you want to change it into gas, you have to break the bonds between this liquid and make gases which have very weak intermolecular forces. That's why all the molecules are very far from each other in the gaseous state. So in order to make these changes, you have to break the intermolecular forces. It is just the forces that hold the molecules to other molecules that break apart. But what are the types of the intermolecular forces? There are three main types of intermolecular forces of attraction. The first type is the dipole forces of attraction. The dipole forces of attraction occurs between polar molecules. So the positive end, like this is a polar molecule. For example, I have O. For example, I have HCl. For example, I have HCl. This is a polar molecule because there is difference in electronegativity here. This is partially negative and this is partially positive. So the difference in electronegativity makes this one a polar molecule. If it comes closer to another polar molecule, similar to it as H and Cl, this is also partially positive and partially negative. There is forces of attraction will happen between the positive end of this molecule and the negative end of the other molecule similar to it, and the positive end of this molecule and the negative of the other molecule similar to it. The molecules which have greater polarity, if the polarity is strong in this molecule, then the dipole attraction will be strong. For example, which one has more polarity, the HCl or the HF? Because F has higher electronegativity, so the polarity is more. The ability of the fluorine to attract the electrons is more than the ability of the chlorine. Why is that? Because fluorine has higher electronegativity. How do we know that? As we go right and up in the periodic table, the electronegativity increases, makes the fluorine the highest electronegative atom and the cesium the least electronegative. Because if you go left and down, then the electronegativity will decrease. This means that the polarity of HF is much more than the polarity of HCl. This has less polarity as a bond and this has higher polarity as a bond, which means that the dipole moment of this one is higher than of HCl. So if HCl comes closer to another HCl, and if HF comes closer to HF, they will make intermolecular forces. The intermolecular forces between the HF and the other HF molecule is much stronger than the bond between the HCl and the other HCl molecule. So the stronger polarity means the stronger, higher polarity means stronger dipole interaction, and it's called dipole because there is a dipole here, partial positive, partial negative. This is one dipole, and the other one is called partial positive, partial negative. So there is a dipole again, and the attraction between one dipole and one dipole. So it's called dipole interaction. The polarity will make a big effect on the melting points and the boiling points of the substances because they increase the intermolecular forces, increase the interaction between the particles, and cause them to have stronger attraction forces. So it takes more energy and heat to melt them and boil them. So this increases. The more you have intermolecular forces, the more you have boiling point, and increase also the melting point. Dipole attractions are relatively weak compared to other intramolecular forces. What are the intramolecular forces of attraction? The covalent bonds and the ionic bonds and the metallic bonds. These are all intramolecular, which are much stronger than the intermolecular forces of attraction. But still, the dipole strength is okay compared to other types of IMF, as we will see in their comparison. So as an example, this is a molecule of NF3. The NF3 is a polar molecule because it is a trigonal pyramidal shape. It makes attraction with another NF3. So as we explained, the N, which is a partially negative of one structure, gets attracted to the F of another molecule. And the N with F, which is partially positive, partially negative. Again, let's do it again. The N, which is partially positive, and this is partially negative. This is partially negative, this is partially negative, and this is partially positive. So the N, which is negative from here, attracts to F from here, and N, which is positive from here, attracts to F, which is negative here. Now, there is a special type of bonds of the dipole, in which the polarity is very strong. These are the ones which are known as hydrogen bonds. So actually, hydrogen bond is a subtype of dipole. There are three conditions for the compound or the molecule to have a hydrogen bond named intermolecular forces instead of dipole. The conditions are the molecule should contain hydrogen atom. It should contain also in the neighboring molecule a fluorine atom or nitrogen atom, only one of them, not all of them. If it's all, it's okay. If two of them is okay, but at least should have one of them, not necessary to have more. And the oxygen atom in the neighboring molecule. And number three, it should have these atoms directly attached to the hydrogen atom, So it is a subtype of the dipole, and we'll see that. And I will see that the partially positive, for example, water is a type of a dipole which has oxygen as a partially negative structure and hydrogen as a partially positive structure, and this will be repeated here. Just copy it and paste it. So just make it oxygen. This is partially negative, and hydrogen partially positive. So the positive of this molecule will be attached to the negative of this one, and the negative of this one is attached to a positive of the neighboring molecule. In the hydrogen bond, the positive is attached to the negative, negative is attached to the positive, same like the dipole. The only difference is the polarity is very strong here because of the presence of the oxygen atom, and oxygen and fluorine and the nitrogen are very electronegative atoms, so the difference between them and the hydrogen is very high. That's why this type of dipole is very strong interaction. That's why it's much stronger. That's why it's much stronger than the dipole. So the strength of the hydrogen bond, intermolecular force of attraction, is stronger than the normal dipole, which has no three conditions. So how to differentiate between the hydrogen bond and the dipole? If you have these three conditions that we mentioned, then it is a hydrogen bond. If it does not have these three conditions, all of them, if one of them is missing, then it will be called a hydrogen bond. No, it will be called a dipole instead of the hydrogen bond. Substances that have hydrogen bonds, such as water and ammonia, for example, they have water and ammonia, they all have hydrogen bond. I have higher boiling point and melting point than substances which are only held by other types of intermolecular forces of attraction, like the dipole, or the other types that we mentioned. So if we compare the melting point and the boiling point of water, for example, which is OH2, compared to SH2, they all have the same structure, the same shape, the same angles, and the same shape of the molecule and everything. But this one has oxygen, which is one of the conditions. This has no oxygen or nitrogen or fluorine, so this condition is not there. So this is not hydrogen bond. One of the conditions is not there, so it is called dipole interaction, and this is called hydrogen bond. That's why the melting point and boiling point of water will be, for example, bigger than that of SH2. In H3 also, it is a trigonal pyramidal, and pH3 is the same shape exactly. This one is considered as a symmetrical shape, so it is polar molecule, but this polar molecule does not have oxygen or fluorine or nitrogen. That's why it's also considered a hydrogen bond, but this one is not considered because it has doesn't have the conditions that we mentioned. Is called only a dipole, and the melting point and boiling point again of this one will be much higher. You need to know that the water is a very dense molecule as a solid. What does it mean that it is dense as a solid? The density of the water as a solid is very high because the hydrogen bonds are very strong, and they form the molecules. They make the molecule join together to form a crystal structure, which keeps them apart than they are in the liquid form. When they are joining, they are apart, not like in the liquid form, they are very close together. So this makes the density of the solid higher than the density of the liquid, and this gives the water most of its properties. If you are asked to draw the hydrogen bond, you need to describe O, attach it to an H. You have to draw another H. You have to draw the partial positive and partial positive here, to draw the partial negative, and draw the intermolecular forces of attraction. The intermolecular forces of attraction, IMF of any type, which is either hydrogen bond or dipole or other types, has to be done only by dashed lines. So don't draw a straight line, it's wrong. It has to be only dashed line. Will be attached to the hydrogen of another molecule, which is partially positive, that's coming from O. Take care, it's not attached to the hydrogen. The O is not attached to the hydrogen of the same molecule. It has to be attached to the hydrogen of the other molecule only. Don't make this mistake. So this is partially negative. The last type of the intermolecular forces is the London dispersion forces. And London dispersion forces is the type of intermolecular forces, sometimes known as LDF, which happens between all molecules. Which means that any type of molecule will have LDF bonding in it. Even if it has hydrogen bond and dipole, it will still have London dispersion forces in it. They are very weak attraction forces, which happens due to the random motion, due to random motion of electrons around the atoms inside the molecules. At a given moment, the nonpolar molecule might have more electrons on one side than on the other side. So this shape is nonpolar, so it's called CH4. CH4 is a nonpolar shape, so it has no dipole structure. Still, at 1 second, you will find that the electrons are revolving and placed in one place more than the other. So at one point, the electrons will be here more than here, which make it an instantaneous dipole. An instantaneous dipole means that it is there for a very few time, very short time, which is meaning it's an instantaneous. And this causes the other part to be partially positive. And when this comes to close to another molecule, the other molecule will see that the electrons are here. So these electrons of the other molecule will come and be, if I have CH4, another molecule, and it finds that the electrons become here for a few seconds, this makes it a very weak negative charge. You cannot say it's negative or partial negative, it's even weaker than that. But this negative will cause the electrons of this one to move away, to be induced to move away also. So this also will be a very small negative, and this is positive. Anyway, if you are asked about the reason of the formation, just say that at a given moment, the nonpolar molecule might have more electrons on one side than on the other side. So this is an instantaneous polarity. That's why it is a very weak dipole. This is a very, very, very weak dipole, which is called an instantaneous dipole-induced dipole, or sometimes known as, or most of the time, London dispersion forces. Because the London dispersion forces depend on the motion of electrons, the molecules which have more electrons will have more London dispersion, or stronger London dispersion forces, and so they will have higher boiling point and melting point. Boiling point and melting point will be higher. The one with more electrons will generally have higher melting points and boiling points. Then the dispersion forces are even weaker than the dipole. So if we want to arrange the types of intermolecular forces according to strength, we will find that the LDF is the weakest, the dipole is stronger, dipole, and the stronger. And the strongest of them is the hydrogen bonding. So although it is a type of the dipole, it is the strongest one. So if you compare the melting point and boiling point of them, of course, this one will be higher as we go to the right. So as you go to the right, the melting point and boiling point will be higher. As you gain more electrons, as we mentioned, the forces of attraction will be more and more significant. So if you compare the boiling point of a nonpolar substance with large number of electrons versus a polar substance with fewer electrons, we can sometimes, it's very difficult to compare it by ourselves, but in sometimes there is no simple rule to follow for that. Like, for example, the water which has hydrogen bonds, it's the water which has hydrogen bonds, its boiling point is 100, and butane, which has only dipole, are nonpolar molecules. The boiling point is 34, which is less than water, but still this one is C8H8, which is octane. Its boiling point is 125. So although it is nonpolar and it also does not have hydrogen bond, its boiling point is much higher than that of water, which is hydrogen bonding. This is because the number of electrons is much higher. So don't say it as a fixed rule, and there is no way to know that. The only way is that if he tells you that, explain why the structure which have LDF sometimes have a stronger attraction forces and more boiling point and melting point than the hydrogen bond, is if this structure has very high number of revolving electrons, very high number of electrons. There is no way to determine that, as we said, but only if he told you, you can explain it. It has very high number of electrons than the hydrogen bond. So this means the LDF is more significant than the hydrogen bond, even and in water. So the role of the London dispersion forces is determined by comparing the molar mass of molecules. However, it's not the mass itself which affects the strength, but the number of electrons depending on the higher mass means higher proton number, so this means automatically higher number of electrons. So the molecule must remain neutral at the end. The molecule must remain neutral at the end. So let's have a look at the strength of the intermolecular forces. We know that the ionic substances are solid at room temperature. If you turn this solid into liquid, you need to break the bonds, which is the bonds of the lattice structure holding them together. The amount of energy needed for this depends on the Coulomb attraction between the molecules. Like, for example, if we have calcium fluoride and you need to break that to make change it from solid into liquid, it has a very high melting point and boiling point due to the presence of strong ionic bonding, and ionic is considered as intramolecular forces of attraction, which is much stronger than the intra, which is much stronger than the intermolecular forces of attraction. It depends on two things. The ionic bonds depends on the charges. So the more charges that you have, if you have +2 or +3, it's better than having +1. This makes the strength of the bondings higher, and also the radius of the ions in the ionic bond. The smaller radius means stronger bonds, and the bigger radius of the ions means weaker bonds. So the covalent, which are liquid at room temperature, will boil when the intermolecular forces between them are broken. For molecules with small size, if I have a molecule of small size, this means that the number of electrons of it is small. This means that intermolecular forces of it will be small, especially the non-dispersion forces. But if it has hydrogen bond, it might be stronger. If it has dipole, or which we'll call the permanent dipole, this will be also strong. And if it has LDF or instantaneous or temporary, we call it temporary or instantaneous dipole, then they will be much weaker, but it will be strong only if it has higher number of electrons. This is the strongest. It's less strong. This is the least strong, and only will be strong the LDF if you have higher number of electrons. But still, the melting point and boiling point of covalent bonds are most always lower than the melting point and boiling point of the solids, ionic solids, because the ionic solids have ionic bonds. And as we agreed, ionic is one of the intramolecular forces, which is much more than stronger than the intermolecular forces, the IMF. You can say that the ionic and the covalent is stronger than the hydrogen bond, which is stronger than the dipole, which is stronger than the LDF. While the metallic bonding, which often involves only one type of metal atoms, tends to be very strong, and thus metals have very high melting points. So if you have metals, you have metallic structure. Metals, you will have metallic bonding. So solids, we said ionic solids. We said ionic solids are very strong because of the ionic bonding. So melting point and boiling point are very high. And the metallic also is very high melting point and boiling point because of the strength of the metallic bonding is very strong. Now let's talk about the bonding and phases. The phase of a substance or the physical state is related to the strength of the intermolecular forces. So if you have solids, the solids have very high strength of attraction between the particles. That's why it has high melting point and boiling point, and the structure is ordered in the form of a lattice. And the liquids have weaker attraction forces, and the gases have very weak or almost none of the solid and gas, and have very weak intermolecular forces of attraction. And the particles are very far from each other, making very big spaces in between the particles. That's why the volume is very big. This means that the substance that have weak intermolecular forces, such as London dispersion forces, tend to be gases. If you have London dispersion forces, which are weak ones, like if you have small number of molecules, you will usually be a gas, for example, nitrogen, while the ones that have strong intermolecular forces are usually like hydrogen bonding, will always be liquid at room temperature, like, for example, water, and the substance that have no intermolecular forces but intramolecular forces, like ionic bonding or metallic bonding, these usually are solids in room temperature, solid at room temperature. What is the vapor pressure? The vapor pressure when you have a beaker, and in this beaker there is closed container and covered, and there is liquid particles inside here, and these liquid particles, if you just heat it, and this one, or due to the normal room temperature, they start to come up, change from the liquid into the gas. So some of the particles start to change from liquid into gas, and they change into gas. And we know that gas particles keep colliding with each other and colliding with the walls of container from inside, causing pressure on the walls of the container. And because this is changed from liquid into vapor, so this is called the vapor pressure. So this is the pressure of the particles of the gas, which are formed from the liquid particles due to the increased temperature. The vapor pressure is one of the most important factors which will depend on the intermolecular forces of attraction, because if these particles are joined together, there are two situations that we have. We can either have these particles joined together very strongly, which means that the attraction forces is very strong between them, so they don't want to leave each other. So if there is strong attraction forces, they don't want to leave each other, they don't want to break apart from each other and change into liquid and change into gas. So they don't want to change into gas. This means that intermolecular forces, they don't want to leave each other and come up. The strong intermolecular forces will cause them not to change into gas. So this means that the gas will be less, means that the vapor pressure will be weaker. While if the attraction forces between them is weak and they don't like each other, they want to leave each other and change into gas. So it's okay for them to change in gas. So most of them will change into gas and form particles. So if they have weak intermolecular forces, they don't want to be with each other, then the vapor pressure will be higher. Why is that? Because the intermolecular forces, because most of the particles will come up and be evaporated. So this means that there is an inversely proportional relation between the vapor pressure and the strength of the intermolecular forces of attraction. The higher the vapor pressure, the less there is intermolecular forces of attraction due to the vaporization of the liquid. And if you increase the temperature, then more of the particles will break apart from each other, and this causes the vapor pressure to be directly proportional to the vapor pressure. So if you increase the temperature, the particles will break apart from each other. So take note of the relationship between the temperature and vapor pressure. Temperature is directly proportional to a vapor pressure, but the vapor pressure is inversely proportional with the intermolecular forces. As you increase the temperature, the intermolecular forces break apart, it becomes less, so the vapor pressure increases as they break free from each other. So if I have two liquids, I have liquid A and I have liquid B, and I have liquid B, and they are at the same temperature. So the temperature is the same, so it does not affect the intermolecular forces. It does not affect the vaporization. So, but the effect of the vapor pressure in this case will depend mainly on the intermolecular forces of attraction. If this liquid has higher intermolecular forces of attraction, the vapor pressure will be less. And if this vapor has less intermolecular attraction, if this liquid has less intermolecular forces of attraction, the vapor pressure will be higher. Now let's try to see how we can make separation for the solution, a solution separation.